Hello everyone, this is K1 from MBT. In this session, we're going to have a battery cell simulation with cooling. In industry, we have 4 different battery cooling methods. The first one is air cooling, the second one is liquid cooling, third one is cooling with heat conducting materials, and the last one is submersion cooling. For each different method, you can see a specified picture on the right side. As liquid cooling is one of the most important and practical cooling methods in industry, we're going to have liquid cooling for a battery cell in this session. So we introduce 2 liquid channels in contact with the active components of the battery cell. If you want to know how to create the battery cell, you can watch my video on the elementary playlist of this channel. So for the liquid channels, we create those in this session. And for comparing the results of how we can get cooling from this cooling channel, we introduce a short circuit condition. As you can see on the right side, we have a short circuit region with the specified values of X, Y, and Z. So after the short circuit condition is started and initiated, the battery temperature will rise, and we'll see how the cooling method can prevent the battery from thermal runaway. So for the MSMD battery model conditions, we have a C rate value of 1, an external resistance value of 0.5 ohm, and a short circuit resistance of 1 e to the power of minus 7 ohm. The total flow time would be 10 seconds and the time step size would be 1 second. So we have a total number of time steps of 10. So now let's go to the Ansys software and start the simulation. So now here we are in the Ansys software. We're going to edit the geometry and create those liquid channels. So we start the design modeler. So as you can see, we have 3 parts, 3 solid parts, 2 tabs, and an active component. We're going to use this face to extrude and create the first channel. So we apply the geometry. For the liquid channel, we must use the add frozen for the operation. The direction would be this edge, but to the other side. And the thickness would be 5 millimeters. And click generate. So this is the first channel. We create another channel for the other side. Apply, add frozen. Direction would be, this is the right direction, and the 5 millimeter for the thickness, and click generate. So now we have 2 channels, but before ending the design modeler, we should select those and make sure that the fluid is selected as the material. So we change the material type to fluid for these 2 liquid channels. So now we end the design modeler and go to the meshing session. So we start the meshing. As in this simulation, we're going to have a heat transfer from a solid to the liquid. We introduce an inflation for the mesh in order to capture the heat transfer accurately and see how the cooling is going to help the battery to keep it from thermal runaway. So, the new geometry is imported to the mesh. We keep the value of element size to 1 e to the power of minus 3 meter. We don't change the sizing, but we introduce an inflation. Before that, we hide this active component in order to select the faces we're going to use the inflation for. So we use the inflation option. For the geometry, we select the channels. This is the first one and the second one. For the boundary, we should select those faces that we need the inflation. You can see all the faces of the channel, but we don't want all the channels to be inflated with boundary layers. So in order to reduce the number of cells and have less computational time, we just select two faces that are in contact with the active zone. So this face of the cooling channel and this face of the other one, and apply. So you can see that two faces are selected for the inflation. For the inflation option, we use a first layer thickness. So now we should define the first layer height. We use a 2e to the power of minus 4 meter for the first layer, and we increase the growth rate as 1.3. And now we can generate the mesh. First, the faces of all the parts are meshed, and then it's going to mesh the solids. So it's almost done. After that, we're going to create new name selections for the channels. We need to introduce 2 inlets and 2 outlets for the cooling channel. So now, if you can see, we just show the other body, and now you can see the mesh. You can see this is the active component of the battery cell, and this is the cooling channel. Near the contact region of the active component to the cooling channel, you can see that we have a fur bonder layer that could capture the heat transfer from liquid to solid. You can create a more precise and dense mesh near the bonder layer, but now for this simulation this is okay, and we're going to keep it for the rest of the work. So now if you want to see how many cells we have almost over 1.9 million cells for this geometry. So now for the name selections, we're going to have the flow velocity inside the channels to the positive direction of the x-axis. So we select these two surfaces to be as the inlets, and create two zones for the fluids in the channels. So we select this channel and create a name selection. We give the name as fluid 1, and this one would be fluid 2. And now we create the name selections for the boundary conditions as inlets and outlets. So this one, as this is the inlet for the fluid 1 channel, we give it a name as inlet 1, and this one as inlet 2. So now we should create boundary conditions for the outlet. So we create a name selection for this face as outlet 1, and this one as outlet 2. So now the name selections are complete. From the last sessions in elementary playlist, we had the positive zone, the negative zone, the cell zone in the middle of the channels, the positive tab as a surface name selection, the negative tab, and now in this session we introduced a fluid 1, a fluid 2, and 4 boundary conditions: inlet 1, inlet 2, outlet 1, and outlet 2. So now the mesh is ready with the new boundary conditions. Now we can start the Fluent Solver to have the simulation. So let's go to the Fluent Solver. Before starting the Fluent Solver, we should update the mesh. It's almost a 2 million cell mesh, so it takes more time compared to previous simulations. If you want to do your simulations with more cells and dense geometries and dense meshes, you should know that you need advanced supercomputers to have those simulations. But with a regular, normal desktop computer or laptop, it's very hard to overcome those simulations with more than 2 million cells. So now we start the Fluent solver. We use double precision and serial for processing. So the Fluent is loading the mesh, and we should wait until the outline view is complete. Now we can see the mesh imported. You can see the boundary layer and the mesh size. We have a fair growth rate for the cells along the Z direction, and that's good. So before we start the simulation, we need to check the mesh. So we've performed the mesh check. You can see that the minimum volume is positive, so everything is okay. We use transient for the time, and as we have heat transfer, we enable the energy. For the solution in equations, you can see that we have the flow and energy together. So now we can introduce the MSMD battery model. So we write define models, add on module, and press enter. We select number 8 for dual potential MSMD battery model and press enter. The MSMD battery model is now loaded, and we can see it in the models tab. We enable the MSMD battery model. We use the NTGK empirical model for the e-chemistry models, a nominal cell capacity of 14.6 amp hour. The C rate would be 1, and for the specified resistance we use an external resistance value of 0.50. In the model parameters tab, we don't change anything, but make sure that the initial depth of discharge is 0. For the conductive zones, we should select the cell zone for the active component and the negative zone and positive zone for the tap components. we actually introduced these zones in the mesh section. So if you want to revise those, you can see our previous video on the elementary playlist. The links are given below in the description. We don't have any busbar components as this is a single battery. For the electric contacts, we just need to select the N tab for the negative tab and the P tab for the positive tab. Those tabs and boundary conditions are also introduced in the mesh section. So now we're ready to print the battery system connection information. So the battery connection info is done. We click OK. And now we need to go to the material section and introduce new materials. So we go to material, we select the aluminum, we change the name to active material and give it a formula of A_M. The density would be 2092. For the UDS diffusivity, we use the U defined per UDS option. So for UDS 0, we select a value of 1.19 e to the power of 6. And for UDS 1, we select a value of 9.83 e to the power of 5. And we select yes for overwrite the aluminum. And this is done for the active material. So if you want to check, the name is okay, the density is okay, and the UDS diffusivity is defined per UDS option. So we need to add another material for the tab zone. So from the material type of solid, we use the copper. We copy the data. And now we have the copper here. So we change the name to tab material. We give the formula as T_M. We use the same density of copper, but we change the UDS diffusivity to user-defined function, and we use a default user-defined function of MSMDBAT. For the electrical conductivity, we use a value of 1 e to the power of 7. Okay, now we check the name is okay. Density is the density of copper. UDS diffusivity is user-defined function. And the electrical conductivity is 1 e to the power of 7. So now we can introduce another material for the fluid. So from the material type of fluid, we select water liquid as the cooling material, and we copy the info. So now you can see the water liquid also added to the materials. Now, by finishing with the material section, we can go to the cell zone conditions and assign those materials to each zone. So for the cell zone, which the type is solid, we need to choose the active material. It's already chosen. For the fluid one, we should use water liquid. For fluid 2, should also use water liquid. For negative zone and positive zone, we should use the tab material. So now we're done with the cell zone conditions. In the boundary conditions, we need to specify the inlet velocity of the fluid channels. So we give it a value of 0.1 for the velocity magnitude, and the same for the inlet 2. So it would be 0.1 meter per second. We don't need to specify any other data for the boundary conditions. Now we can go to monitors. For the residuals, we use an absolute criteria of 0.001 for all the equations, the continuity, momentum, energy, and potential. For the reports, we define 2 report plots, one for the temperature and the other one for the potential. So for the potential, we use an area weighted average. We give it a name as phi plus. From the field variable, we select the user-defined scalars. The potential phi plus is already selected, and for the surfaces, we use the cell zone. We report the file, report the plot, and print to console. And click OK. So now we can see we have the phi plus reports. Introduce a new one for the temperature of the cell zone, but we use the maximum temperature. So we need to define a surface report of facet maximum. So we give it a name as cell max temp. The report type is facet maximum. The field variable would be temperature and static temperature, and the surfaces would be the cell zone. So we report the file, report the plot, and print to console. And click OK. Now we have the cell max temperature plot. Now we're ready to go to initialization. We used a hybrid initialization, but before initialize the solution, we need to define the circuit, the short circuit condition. So in the domain tab, we use adoption controls. We define a new cell registers, and it would be a region. We should define the region that the short circuit condition is occurred. We need to define the X, Y, and Z ranges. So for the X, use a value of minus 0.01 to a value of 0.01. For the Y values, it would be 0.08 to a value of 0.11. The Z value would be the thickness of the active component, and it would be from 0 to 0.002. If you want to make sure about these values, please check the geometry creation for the battery cell and tabs from the elementary playlist, and check the geometry details. We name this region as short circuit and save it. So, okay, now we initialize the solution. For the boundary conditions, you can use different values for the outlet. You can specify outlet pressure. But in this simulation, the aim is not checking all the boundary conditions. So in another simulation that you're going to have in the future for validating an experimental situation, you can use different values for the boundary conditions depending on your experimental conditions. So the flow initialization is done, and now the Fluent Solver is initializing the battery model. So the battery model is also initialized, and now we can patch the short circuit region. So for the variable, we use short circuit resistance value, and we give the value of 1e to the power of minus 7, and the registers to patch is the short circuit region. So if you have watched our previous video on short circuit treatment, you can see that the same amount of cells are marked compared to that simulation because we have selected the same region. And close. Now we're ready to run the calculation. The number of timer steps would be 10. The timer step size would be 1 second. And we increase the maximum iterations per time step to 30 for this simulation, and we click calculate. As this simulation is gonna take more time compared to previous simulations, we come back when the calculation is finished. So the calculation is complete. As you can see, the potential decreased over the first seconds, and then at a constant value over time, the maximum temperature of the cell has been increased drastically over time. If you want to look at the contours of temperature, we can select temperature and static temperature and define a new surface or plane. That would be a plane in the middle of the cell. Let's the Z values be all 0 and we call it mid cell and create. Okay, now we have the mid cell plane and we display the contours. Let's see. Okay. You can see that the temperature goes up to 354, and as this is obvious, the heat diffuses along the X direction because the water direction is in the positive X direction. If we want to look at the channels and temperature on the boundary layer, we can define a new plane. This must has a Y value of 0.095. We copy this for all other Y values. And create. This would be another plane and display. So now we have that plane here. Okay. Now we can zoom in and see. Here, this is the active component of the battery, and here is the water channel. You can see a very thin thermal boundary layer that most of the water is at the same temperature of 300 Kelvin. But in the boundary layer, you can see a temperature rise for the water. As long as a bulk part of the water is not affected by the temperature rise, so the cooling method is okay and it's doing good. Now you can see better how temperature is actually the heat generation is diffused and taken away from the core of the battery. Okay, now we're finished with the simulation, and let's see how this cooling method helped us from keeping the battery from thermal runaway. We should compare these results with the same results from another simulation without cooling channels. So if you want to get that simulation data, you need to simulate the battery cell without the channels with the same input data as the short circuit condition and the short circuit region, with the same external resistance value and with the same short circuit resistance. So you can do that on your own. And just now we compare the results and see how this cooling channel helped the battery to keep it from thermal runaway. So as you can see here, we have done both the simulations without cooling and with cooling with liquid cooling channels. As you can see, for the maximum cell zone temperature, which is actually the faces of the cell zone and not the inside of it, we have a temperature rise up to 430 kelvins for the case without cooling and just 10 degrees for the case with cooling. So here you can see that we have achieved a very good performance with the case with cooling channels. And as you may know, the thermal runaway of a battery cell may occur between temperatures of 130 to 200. So in the case without cooling, the battery has a good potential to face this thermal runaway condition. On the right side you can see the potential of the cell zone. So in the case with cooling channels, the potential after a short drop in the first second is plateaued and there is not much change in the potential value, but the case without cooling, the potential value increased over time. And that's one of the reasons that we had increase in the temperature of the cell zone. So this is all for this simulation. I hope you enjoyed this video. If you liked, please give it a thumbs up and share this video with your friends. If you have any questions, please leave in the comments. I will get back to you as soon as possible. Thank you all.